everyone, and welcome to the Physical Geography 100 Lecture Podcast Series. I'm your instructor, Brian Krause, and today we're going to begin Chapter 3, which introduces the composition and structure of the atmosphere. So in this mini-lecture, like all the mini-lectures, I'm not going to cover all topics or ideas presented in the text. Rather, my aim is to highlight a few of the key ideas and then discuss them in a bit more detail. In this lecture podcast, I've included concept check in the form of non-graded quizzes that are at the end of this lecture. So the atmosphere that envelopes us reflects this complex interaction between the four different environmental spheres that we've discussed in previous lectures. And due to the Earth's gravitational pull, we can see here in this slide that 50% of the atmospheric mass can be found within 3.8 miles above sea level, and 98% within 16 miles of the sea level. So as you can see, this area that we can live in is not very high in terms of elevation. So when we first begin to talk about the atmospheric composition, we can divide this into two broad regions that can be identified using air composition as a means of subdividing the atmosphere. The heterosphere is the outermost sphere where gases are distributed in distinct layers by gravity according to their atomic weight. So extending from an altitude of about 50 miles to the lightest elements, which is hydrogen and helium, are found at the outer margins of the atmosphere. And the heavier elements, nitrogen and oxygen, are found at the base of this layer. The homosphere lies between the Earth's surface and the heterosphere, and gases are nearly uniformly mixed by turbulence through this layer, even though density decreases with height above the surface. When dealing with atmospheric composition, there's something called permanent gases, and it's nitrogen, oxygen, and argon are called these permanent gases because their concentration has remained virtually the same for much of recent Earth history. And the three most important abundant gases in the atmosphere are nitrogen, which makes up more than 78% of the total, oxygen, which makes up nearly 21%, and argon at 0.93%. So you should know what these permanent gases are and these percentages. Nitrogen is a relatively inert gas. Inert means it doesn't react with anything, and it's produced primarily by volcanic activity. It's an important component of meat, milk, eggs, and other tissue of plants, especially grains and members of the pea family. It can't be ingested directly by organisms, but made available to plants and then to animals via compounds in the soil. Oxygen is important for plant and animal respiratory processes. It's also important to chemical reactions oxidation that breaks down rock materials like chemical weathering, which we'll discuss in the coming chapter. Without oxygen, things can't burn either. Free oxygen in the atmosphere is produced, or as I should say, as a product of plant photosynthesis. Plants take up carbon dioxide, and in the process of photosynthesis, they release oxygen. Argon is a colorless, odorless, relatively inert gas, and the reason it is used for, like, for example, electric light bulbs, fluorescent tubes, is used to form inert atmosphere of arc welding and growing semiconductor crystals. The next thing is variable gases. So we had the permanent gases, and now we're going to discuss the variable gases. And these so-called variable gases are those that are present in small and variable amounts. These include carbon dioxide, methane, ozone, water vapor, and particulates, among others. Even though they represent a tiny portion of the atmosphere as a whole, they exert a great control over our environment. So first, let's look at water vapor, and it's an extremely important gas found in the atmosphere. It can vary from 4% in the steamy tropics to nearly non-existent in the cold, dry regions of the Arctic. Water vapor is also a good absorber of Earth's outgoing radiation and thus is considered a greenhouse gas. So we'll be talking more about greenhouse gases in the climate debate. So when water vapor is converted to a liquid during condensation, clouds are formed. Clouds are a good absorber of radiation given off by the Earth's surface, and the absorption of this energy raises the temperature of the air. But clouds are generally light-colored and hence reflect incoming solar radiation off their tops. The reflected light is sent back to space, never reaching the ground to warm Earth. Carbon dioxide makes up only 0.039% of the atmosphere by volume, and carbon dioxide is essentially a synthetic process of plants. So huge quantities of carbon are stored in plant tissue, deposits of coal, peat, oil, and gas. Carbon dioxide in the atmosphere varies throughout the year, though, decreasing slightly during the summer as plant leaves out, and then increase during the winter as plants go dormant and the photosynthesis decreases. Finally, we can look at ozone. Is both beneficial and harmful to life on Earth. Much of the ozone in the atmosphere is found in the stratosphere, and here ozone absorbs UV light from the sun and it prevents it from reaching the surface. Without this blanket, humans would be exposed to serious sunburn and potential risk of skin cancer. Ozone is also found in the lower layer of the atmosphere called the troposphere, and here ozone can be act as an eye irritant and a respiratory irritant as well. So the final part of the atmospheric composition that we'll be talking about are particulates and aerosols. And the solid and liquid particles that are found in the atmosphere are kind of collectively called particulates or aerosols. And particulates and aerosols play several important roles in the atmospheric process. Particulate matter includes such things as dust, dirt, soot, smoke, and tiny particles of pollutants. Major natural sources of particulates are volcanoes, fires, wind-blown soil and sand, sea salt, and pollen. Human sources such as factories, power plants, trash incinerators, motor vehicles, and construction activity also contribute to particulates in the atmosphere. And particulates are very effective at filtering the energy and moisture balance of the Earth system. Particulates can diffuse sunlight, reducing the amount and intensity of solar radiation reaching the Earth's surface. The most spectacular sunrises and sunsets are a result of this light being refracted from particulates in the atmosphere. And particulates will also reflect sunlight back out to space, never letting it reach the surface of the Earth. Decreasing a significant amount of incoming solar radiation can cause global temperatures to decrease. The eruption of Mount Pinatubo back in 1991 caused a 0.5 degrees Celsius decrease in global temperatures. And so that's a significant amount. And however, particulates can also absorb long-wave radiation emitted by the Earth, causing the atmosphere to warm as well. So they can have both effects. So now let's kind of look at this vertical structure of the atmosphere. So if we examine the vertical structure of the atmosphere in different places, we'll find it varies in height, being the lowest at the poles and the highest at the equator, and varies between summer and winter months. The varying height is due to this spatial variation in heating of the Earth's surface and thus the atmosphere above. This makes it difficult to define the exact height of the layers of the atmosphere, and the solution is to subdivide the atmosphere not on the basis of fixed heights, but on temperature change. So here in this figure 3-5 in your text, and shown here, illustrates the way in which the atmosphere is divided using temperature change as a primary criterion. So a quick note before you look at these different layers, we will use the name sphere when we talk about an entire layer, and a pause name when we are interested in either the upper portion of the layer or boundary between layers. So first is the troposphere, is the layer closest to the Earth's surface. The graph of temperature change indicates that air temperature decreases with an increase in elevation throughout this layer, and that's important. Air temperature normally decreases with height above the surface, but the primary source of heating of the air is the Earth. And due to the length and angle of incoming solar insolation, the troposphere is deepest over the tropical regions and shallowest over the poles, and deeper in the summer than in winter. Above the tropopause lies the stratosphere. Although most of the stratosphere, the air temperature increases with an increase in elevation, creating a kind of a temperature inversion. And this rise in temperature is due to the presence of the stratospheric ozone, which is a good absorber of this ultraviolet radiation emitted by the sun. As energy penetrates down, less and less is available for the lower layers, and hence the temperature decreases towards the bottom of the stratosphere. Next is the mesosphere. Air temperature begins to decrease with increasing altitude. And about 99.9% of the gases that comprise the atmosphere lie below this level. The air of the mesosphere is thus extremely thin, and the air pressure is very small. So with very few particles like ozone capable of absorbing solar radiation, especially near the top of the layer, the air temperature decreases with height. Temperature increasing with increasing altitude in the thermosphere. Here, energetic oxygen molecules absorb incoming solar radiation, raising the layer's temperature. So as these oxygen molecules become excited, bouncing around, they are raising the temperature there. And because the solar activity determines the temperature of the layer, temperature at the top of the layer is warmer than the bottom of this layer at the thermosphere. So you should understand these different layers, and if the temperature is going up and if it's going down. You don't need to know the exact altitude that these are happening at. You just need to understand what is going on in each one of these spheres. When discussing the vertical structure of the atmosphere, we also have to discuss the atmospheric pressure. And atmospheric pressure can be thought of as the weight of the overlying air. Therefore, the taller the column of air above an object, the greater that air pressure exerted on that object. Because air is highly compressible, the lower layers of the atmosphere are compressed by the air above it. And this compression increases both the pressure exerted by the lower layers and the density of these layers. So the higher you go, the air's pressure decreases. So if you go high enough, for example, you climb a very tall mountain, you will begin to feel the effects of lower air pressure and density. So as air pressure decreases, oxygen continues to account for 21% of the gases in the air as it does at sea level, but there is less oxygen because there is less of all of the air's gases. So for instance, by the time you go about 12,000 feet, the air pressure is about 40% lower than at sea level. This means that with each breath, you're getting about 40% less oxygen than at the lower altitude. So this is why you get winded when you climb stairs at higher elevations. So now let's turn our attention to weather and climate. So what's the difference between weather and climate? It's a matter of time scale. Weather is day to day. Weather is highly variable. So on Thursday, it might be good weather, and on Saturday, it might be bad weather. The climate can't be harsh on Thursday and mild on Saturday because it's not measured in this terms of days, but measured in terms of many, many years. So the weather can change in an hour, say when a cold front moves in, bringing Arctic air, suddenly making it freezing cold, or on a summer day, the barometer might fall, announcing the arrival of some low-pressure center in a rainstorm that is not far behind. In contrast, when we say the climate has changed, we make a statement about a long-term shift from cold to warm or from dry to wet or vice versa. So when we're talking about climate change, we're talking about, decades of time here, not just day to day. Now that we've defined what weather and climate is, now we want to look at the four important elements of weather and climate, and they are temperature, moisture content, pressure, and wind. And changes in these four elements are driven by several controls, which we'll look at in the following slide. These controls are interrelated, and they drive changes in the elements and lead to weather and climate. And so by understanding these four concepts, we can begin to understand the complexities of weather dynamics and climate patterns. In the previous slide, I mentioned the elements of weather and climate, and these are listed in the left column of this table. So now we're going to take a closer look at the right column that deals with the controls of weather and climate. So let's first look at latitude. And Earth's surface and atmosphere receive varying and changing amounts of energy from the sun. And generally, the areas around the equator receive more energy or incoming solar radiation, while the pole areas receive less. Therefore, areas of lower latitude tend to be warmer, and pole areas tend to be cooler. Because of this, latitude is the most fundamental control over climate. Next is land and water. And because land and water heat at different rates, land heats and cools much quicker than water. While the areas kind of near large bodies of water tend to have their climates moderated. A lot of people say if they live kind of near an ocean or a very big body of water, that these are their thermostats that kind of regulate the temperatures from having any extremes. And that means that in general, areas along the shoreline will have milder summer and winter temperatures. And also, bodies of water such as oceans provide lots of moisture for the atmosphere. And this is especially true about warm bodies or currents of water. The next, circulation of the atmosphere is constantly distributing cold and warm air across the Earth, and we will discuss that in greater detail in the coming chapters. Circulation of the ocean. There's a broad general circulatory pattern of the ocean that aids in the transfer of heat by moving warm water poleward and cool water equatorward. Altitude. Generally, the higher you go in the lower portion of the atmosphere, temperature, moisture, and air pressure decrease. Topographic barriers, such as hills or mountains, can alter wind flow. Because winds can be forced upward by an elevated landform, this exposed or windward side can often have a different weather and climate than the sheltered or the leeward side. So as air travels up a mountain, this moisture is squeezed out of the air as it cools, condenses, and falls as precipitation. And air temperature and the amount of moisture in the air are usually decreased as it kind of then flows back down the leeward side of the mountain. And we'll be discussing more of that in coming chapters, as well as your lab manual. When you do your lab, this will be an exercise. And finally, storms. All storms basically create specialized weather circumstances, and so are considered to be a control as well. So that concludes this lecture on Chapter 3. The following slides are these quizzes that I've set up for you. So once again, if you kind of take these quizzes and you do well on the quizzes, you should